So unlike the previous 3 days, I think that since this is the day for my fourth lecture, I should immediately start the fourth lecture. Except there's one thing I have to tell you first. So, you know, I talked before about this picture where in random KSAT you have, I'm not even going to draw anything, where you have this large range of densities where we have many clusters of solutions, where each cluster has many frozen variables, where the clusters have big energy barriers between them. And I said that, you know, we think that in this range it's exponentially hard even to find a single solution to a random KSAT problem. And indeed, there was an attempt to prove that P and NP are different using the properties of the landscape of random KSAT. But this doesn't really make sense because, as one of you brought up with me at lunch yesterday, there's another problem which is very similar called XOR-SAT. So XOR-SAT stands for exclusive OR. And so here, the types of constraints, rather than saying this is true or that's false or that's true, instead they say something like this Boolean XORed with that Boolean XORed with that Boolean is, say, 1. And to translate this into terms you might be more familiar with, this is simply saying that an odd number of these variables is true, okay, as opposed to saying at least one is true, which is what SAT wants. And the thing is that if you look at the landscape of this problem, it's very similar to the KSAT landscape. There's a clustering transition, there's a freezing transition, it gets very bumpy. And indeed, if you try to do Monte Carlo, you know, flipping individual variables, it takes exponential time to get from one cluster to another, and so on. And yet, this is a linear equation. It happens to be a linear equation mod 2, but it's still just a linear equation. Okay? And so if I have a formula consisting of a whole bunch of these linear equations, you can solve it using Gaussian elimination, right? Using high school linear algebra. So the point is that even though the landscape is bumpy, this problem is quite easy to solve in polynomial time. And this goes back to the point we made on in the first lecture, that when we talk about a landscape, we're also implicitly assuming a notion of neighborhood. And indeed, if the only types of algorithms that are available to you are local algorithms, algorithms that are changing a small number of variables at a time, those algorithms will get stuck. What you do in Gaussian elimination is you say, gee, you know, I would like to subtract one equation from another, and you're essentially doing a global redefinition of your variables when you do that. When you have this whole matrix of constraints, of coefficients, and you subtract one row from another to make the matrix simpler, you're saying, gosh, well, I would rather not think of the problem in terms of the original variables. I would instead like to think of the problem in terms of new variables, which are linear combinations of the old variables, and now the problem becomes much simpler. And the point is, you know, so saying that a landscape is bumpy does not necessarily mean that it's hard to move around on it. On the other hand, we believe, but don't know, that there is no analogous, miraculous redefinition of the variables for KSAT, which enormously simplifies the problem. So, but we don't know that. And you could boil down the P versus NP question if you wanted as saying that we don't know that, but we think there's no such thing. Yes?
Is there an easy kind of heuristic way of seeing why you can't map KSAT to XOR-SAT? I mean, they have a lot of the same features, but there's something that's fundamentally different, right?
Yeah, I mean, I think this is interesting because viewed as p-spin models, if you wrote these down as Hamiltonians, in both cases, you would have these cubic terms involving the spins. And I think this is kind of a case where there's this group theory structure to these clauses, this linearity, mod 2. that sort of the Hamiltonian doesn't know. Now, to be fair, that linear structure only exists in the zero temperature case where we're demanding that all of these constraints are satisfied. And if you were doing this at non-zero temperature, then I think it would be just as hard. And indeed, there is a problem in computer science called max XOR sat, where we abandon trying to satisfy all of the constraints, but we try to satisfy as many as possible, and that's NP-complete. So somehow this beautiful linear structure that makes the problem easy only exists in the zero temperature case where we're asking, is there a zero energy frustration-free ground state, and if so, can we find it? Okay, so as sort of at that extreme, I mean, from the physics point of view, that's a very special case. At that very special case, this beautiful mathematical structure takes over that makes the problem easy. So, yes?
Would you say the K-set is a system of nonlinear equations?
Well, yes, but I'm also trying to say that, you know, physics doesn't know about adding mod 2 somehow, right? So when you say something is linear, well, linear in what group? Linear with respect to the reals? To some finite field, you know, and a problem which looks nonlinear might turn out to be linear in some other algebraic sense, right? So, yeah, anyway. So we cannot assume just because we understand the physics of a landscape that we understand the computational hardness of a problem, because there are these sort of very, if you wish, unphysical algorithms that work some of the time. All right, but now I'd really like to start the fourth lecture. If I, you know, this is my last chance to bring this lecture series in for a landing, so I better not digress too much. I'm going to remind you of our notation for the stochastic block model. We have k groups of vertices. If I have a vertex I, then I define sigma I as it's the label telling us what group it belongs to. And then the probability, when I generate the random graph, the probability that two vertices are connected is going to be 1 over n times c sub the type of I comma the type of j, where c is a k by k matrix. I'm going to focus on the special case where c sub r s is c in if r equals s. So those are the diagonal entries of this matrix. The density of edges between vertices within the same group. C out if they belong to different groups. And then I defined this quantity lambda, which is C in minus C out divided by KC, where C is the overall average degree, the total average number of neighbors each vertex has, which is you have C in over K on average within your group. You have C out over K on average in each of the K minus 1 other groups. And this lambda, which is sort of our measure of the strength of the community structure, is also the second eigenvalue of the matrix we get when we take this matrix and normalize it to be doubly stochastic. We can write that as lambda times the identity matrix. That takes care of the diagonal entries, plus 1 minus lambda times the flat matrix. J here denotes the matrix of all ones. And again, viewing this as a transition matrix to go from the type of I to the type of a given neighbor J, this says that with probability lambda, you copy the label from I to J, and with probability 1 minus lambda, you choose a label for J uniformly at random. Okay, so that was our notation from yesterday. this? I'm just pointing out that if I normalize this matrix of edge densities to make it a stochastic matrix, so I mean the column sums here, if you see that's Cn plus k minus 1 times C out, which is k times the overall average degree. So I divide by that column sum. This becomes a stochastic matrix. And I can write that stochastic matrix as a linear combination of two very simple stochastic matrices, the identity and the flat matrix, whose entries are all 1 over k. And the coefficient of the identity is also the second eigenvalue of this matrix. I'll leave that as an exercise for you. And that is equal to that. Yes?
Second eigenvalue, or?
The first eigenvalue is of a stochastic matrix is always 1. Whereas this...
Probability thing, it's I and J are in what? I just can't read the letter correctly.
This is, this is the probability, this is sort of graph theory notation. This is the set of edges. So this is the probability that there is an edge between a vertex I and vertex I and vertex J. Yes?
So I keep thinking about like just a percolation model. So if we set C out equals to 0, this would group the vertices that are connected into like different groups, right?
Right. If C out is 0, then you may only be connected to others in your own group. And so within each group, we would have just a random graph.
Mm-hmm. Okay.
Yeah. Good. And now, this is a planted model of random graphs. So again, the idea is that I have a true community structure, and I build the random graph in a way which is correlated with that true community structure. And again, the goal is, given the graph, I want you to try to find that planted configuration, sigma, that is that tells us what group each vertex belongs to. Okay? But there's another graph, another family of graphs that this could have been, which is what I'll call the null model, or the unplanted model, which is just the Erdős-Renyi random graph. It's often notated G comma NP, where P here will be C over N, where C is our average degree. And this is the graph where there is no community structure, and every pair has an edge between them with probability P, period. So the difference between the two is that in the block model, the probability of an edge depends on the type of the endpoints. Here it's the same for all pairs, so there is no real community structure. So one question is, like I mentioned at the end of last time, if I generate a graph, can you tell how I generated it? Which of these two models I used? Okay? And intuitively, if you can't do that, if you can't tell if communities exist, then you also are going to have a lot of trouble finding the communities if they do exist. And it turns out, it's not totally obvious, but it turns out that the thresholds for these two tasks are indeed the same. Okay? Good. Now, the other thing I wrote down before is that if we assume that all labelings are a priori equally likely, then the probability of the label given the graph is proportional to the probability of the graph given the label. And so if we think of this as e to the minus a Hamiltonian with unit temperature, sorry, maybe you can't see this from over there, then we get a Hamiltonian which is just the sum over all pairs of a coupling which is ferromagnetic if Cn is bigger than Cout. So we get what, in physics terms, we would call the ferromagnetic k-state Potts model, just the generalization of the Ising model, where we have k possible states at each vertex instead of 2. And one thing I want to point out is that, of course, we can define this spin system on any graph, including a graph generated without any community structure. Okay? So the game we're playing is, we have this graph, we define this spin system on it, we study the physics of that spin system, and based on that, we want to know when does this physics tell us whether there are communities or not, and if there are, when do we get from this Gibbs distribution, when do we typically get states which are correlated with that true state? Okay, so kind of the difference between what I've been talking about and, for instance, what Giulio has been talking about is that we're used to this picture that there are many clusters of states, but now one of them is the true cluster, okay, that is built around this true underlying state. And then the transitions we're interested in are, when does that true cluster dominate the thermodynamics? Okay, there was a question back there first. Sorry.
Can you explain that proportionality again?
This one, well, so Bayes' law says that the probability of, if I tell you, if I fix one variable, then the probability distribution I get on another variable conditioned on this one is the probability of this pair overall divided by the total probability of the second one. But this is also the probability of B given A times the probability of A divided by the probability of B. So the picture here is that if B is the graph, okay, then once we fix the graph, this is just a constant. And if A is the labeling, then if I choose all labels to be equally likely, a so-called uniform prior, which I'm doing for simplicity, then this is also a constant. And so up to normalization, these two things are equal. Again, if you think that the groups are not the same size, or if you have some side information or metadata saying, I think that he's probably in group 3, physically that would be an external field. In terms of Bayesian inference, we would put a higher prior probability on you being in group 3. And that would alter things a little bit. Okay, there was a question over there. You? No? Not anymore? Over here, yes?
Yeah, just a clarification. The sum of the Hamiltonian, the sum over edge in the graph.
Yes, these are just the neighboring pairs. And if you recall, I waved my hands and said there's also a weak global term for all pairs, or for the non-neighboring pairs. But in order to save chalk, I will not usually write it down. Okay, but for instance, it prevents us from putting all of the groups in the same group. It prevents us from, if we literally just took a ferromagnet, right? A ferromagnet would be very happy if everybody was in the same group. Okay, so those weak global anti-ferromagnetic terms would prevent that. Okay, good. All right. Now, putting your physics hat on, how might you solve this problem? And let's say that your real goal here is, for instance, to compute what we'll call the marginals and what you are probably used to calling the magnetizations. So the marginal, mu stands for marginal, I will write this and that And this is just shorthand for the probability that a particular node belongs to a particular group. Okay? Because ultimately, you know, I mean, some of you are in group 1 with probability 99%, but some of you are in group 1 with only probability 60%. I want to know that because I want, again, if we're doing Bayesian inference, we don't just want the ground state. We don't just want the most likely labeling. We want some sense of the entire distribution because we want to know how certain we are about things. Some of you I'm not so sure about. Okay? Others I'm very confident. So we want to understand these marginals. Now, you're probably thinking, well, wait a second. Everything here is symmetric under permutations. And so, well, actually, everybody is equally likely to be in every group because if we permute the groups, nothing changes. And you're right, but immediately after thinking that, you thought that, well, this is just like the Ising model below the transition temperature. I can break the symmetry by, you know, fixing a couple of spins or, you know, just choosing a macro state in physics terms. And you were right when you thought that second thing. Okay? And that's all that we need to say about that. But it's true that if we have k groups, then just as in the standardizing model, when we have the mostly up state and the mostly down state, we have, you know, k factorial clusters, each of which corresponds to a permutation of the original labeling. Okay? All right, good. Now, let's discuss belief propagation, 1 through 4. So, certainly one way to compute these marginals, which is the way that we're most familiar with, is by Monte Carlo sampling. Okay, so we could run around flipping the spins, the labels of individual vertices at every step, choose a random vertex, compute if the probability distribution of its label, given the current labels of its neighbors, that would be so-called heat bath sampling, or you could do metropolis sampling, where you choose one candidate move to make and either do that or don't do it. And you're probably familiar with those methods. They would eventually work, but I claim that they would actually be rather slow. And I want to do something faster that is also better in practice, but also will give us a lot of theoretical insight. And that's belief propagation. So belief propagation goes back to the work of Judea Pearl in the AI and machine learning community. And I think it's fair to say it was kind of rediscovered, in a sense, in statistical physics under the name the cavity method. But they're a little bit different. I'm going to describe belief propagation as an algorithm that you would run on a particular finite graph. And then other people coming after me, like I think Guillaume and Florent, will talk about what we typically mean by the cavity method, which is thinking about what belief propagation does on large random graphs. Okay? So I'm going to describe it as a concrete process on finite graphs. So here's the idea, and it's very clever. And I should say that I tried to learn belief propagation multiple times, and I found it rather difficult. This is a very simple setting in which to learn it, and with maybe somewhat fewer subscripts and superscripts. So here's the idea. Instead of just trying to compute this marginal, we instead think of each vertex I as sending a message to each of its neighbors j, which is an estimate of I's marginal. So this is what I tells j is the probability that I belongs to group R. But the clever catch is that I can tell different things to different neighbors. Okay? And indeed, when I computes the marginal, the message that it sends to J, it will base that only on the inputs it receives from its neighbors other than J. And this corresponds to the cavity method because we imagine, well, what if we had an atom in a crystal or whatever, and this atom was not here? Then there would be fields in this empty space caused by the other vertices. And then in turn, if this was not here, there would be fields in that empty space caused by fields created by the other vertices. And then we'll try to make everything self-consistent. Okay? So that's the basic idea. Now, how does I compute this message? Well, you're all familiar with, for instance, the vanilla. I'm hoping you're familiar with the vanilla mean field approximation for the Ising model, for instance. It's almost like that. We're not simply going to add up the average fields. We're going to do something a bit more probabilistic. Really, what we're going to do is simply Bayes' rule. Okay? So remember that if you and I are more likely to be connected when they're in the same group, if we are connected, that makes it more likely that we're in the same group. Okay? That's what creates this ferromagnetic interaction along all of the edges. So, and we kind of already said this here. What is the probability that J is in the same group as I? Well, it's there's this 1 over k. We have this baseline that everybody is equally likely to be in every group, but then there's this term here for being in the same group. So let me write it in the following way, and then we'll fill more of this in. Suppose that one of I's other neighbors, L, which I wanted to call K, but I already used that for the number of groups. Sorry. Haven't you ever wished that, like those posters that have the electromagnetic spectrum, and like down here is infrared, and then up there is gamma rays, and in between is visible? We should have one of those for the alphabet, right? So like I, J, and K are vertices, unless U, V, and W are. F, G, and H are always functions. Okay, all right. Someone should make that poster. So suppose that one of I's neighbors, L, says to I that L is in group S. Okay. Well, there is an edge between them. And there is an edge between them with probability C sub Rs divided by n, which is just a constant. And so Bayes' rule would weight this message by the probability that that edge is there. Okay. But L could be in any of the groups S. So to get the average, what people would call the Bayes factor, the average weight by which the probability that I is in group R would go up or down, we have to sum there. And then we are going to get this Bayes factor from all of I's different neighbors. So we're going to take the product over, let's see, how do you want me to write this? L is in the neighborhood of I, but it isn't J. You okay with that notation? And then we need to normalize. And rather than writing 1 over a normalization factor, I will just use this symbol for is proportional to, which is easily mistaken for an alpha.
Mu IBJ is probably of sigma I equals to R, given that condition
I mean, really what's going on here is we're just saying that the probability that I belongs to group R, given that L belongs to group S, and that there is an edge between them, okay, is proportional to the probability that there is an edge between them, given that sigma I belongs to group R and sigma L belongs to group S. And that's up to a factor of 1 over n. That's C sub rs by definition of the model. So this is just Bayes' rule. Okay? So if you've already seen the cavity method in the spin glass context, you probably think of it as combining fields. But we have our Bayesian inference hats on, so we're going to think about it in terms of multiplying probabilities, okay, and multiplying average reweightings of probabilities based on what we know, because that's what Bayes' rule does. Every time we learn something new, we reweight our probability distribution, and in this case, you can think of it as learning that there's an edge here and that this is in a particular group. That changes the probability here. Then we learn about this edge in this group. We learn about this edge in this group. Okay?
Is that really crucial to exclude J?
It turns out it is, and if I have time, I'll describe. I mean, there's another version of this. A different variational method, which is more naive, where we would take this away and take that away, okay, and take that away. And then you would be doing something closer to, I would describe it as kind of classic mean field, right? I mean, what do you do when you first see the Ising model? You say, well, I'll say that the spin here is a function of the spins of all the neighbors. You don't do this thing of telling one neighbor something based on the ones other than it. That corresponds to assuming, though, that the Gibbs distribution is a product distribution. It corresponds to a so-called variational method where we assume that the joint distribution is just a product of all the individual distributions we get from these marginals. And then under that assumption, you try to find the best marginals, where best means, okay, now I'm going to say it, minimizing the Kullback-Leibler divergence between that product distribution and the true Gibbs distribution, which in physics terms is minimizing the difference in their free energies. Okay? Okay, so let me describe the... so I'll come back to this. And are you guys going to talk about the beta free energy? You have to, right? Okay. All right. Someone will clean up my mess and talk about the beta free energy. Well, so first of all, let me just tell you about what belief propagation is as an algorithm. Okay? But first I have to tell you something really important that you may be thinking to yourself. What I did here was I averaged over the messages, the weighted messages from each neighbor, and then I took a product. But that's like assuming that whether this belongs to a given group is independent to whether this or this belongs to a given group. It's not like assuming that. It is assuming that. So this assumption is called conditional independence because, strictly speaking, it's only assuming that my neighbors are independent if you condition on my own state. To put it differently, it assumes that my neighbors are correlated only because, and only to the extent that, they interact through me. Okay? Which means that we're assuming that this is a dilute structure with very few short loops, Because if I have a short loop, or especially a triangle, then these two are directly correlated with each other. And then this would not be a very good approximation. Okay? So if you're interested in thinking about real networks, well, real networks are full of triangles. And indeed, in that case, this is just systematically off, or, well, by which I mean off. We're not sure in which direction. I can tell you two things. I can tell you that from a theory point of view, if we're thinking about random sparse graphs, those are locally tree-like in the sense that if you look at any constant radius around vertices, almost all vertices, their neighborhood out to that radius is a tree. And then if you believe that correlations decay with distance somehow, if the shortest path connecting these is rather long, say log n in length, then you might hope that this is asymptotically correct, that the correlations due to these longer paths are small. And making this rigorous is a matter of active research, and in a number of settings we can show that this is rigorously true, asymptotically. That's the theory answer. The practice answer, if you're interested in actually running this on real, say, social or biological networks, is that in practice it seems to work pretty well, and is fast. That's all I can tell you. So yes, there are lots of short loops, and that will create correlations that this method does not take into account, but it seems to work pretty well anyway. Okay. All right. So what do I mean by work? What I mean is start by initializing these messages randomly in some way, and then repeatedly update them. You can do it synchronously or asynchronously by updating everybody's message to all their neighbors based on the previous messages they received from all their other neighbors. And keep doing this until you reach a fixed point. You might never reach a fixed point. If you do reach a fixed point, it might take a long time. And if and when you do reach a fixed point, these might be terrible estimates of the marginals. But sometimes it converges quickly and it's accurate. And in some theoretical settings, we can show that it will. Okay? That's belief propagation. What's your question?
When you say we initialize these messages randomly, what do you mean?
It kind of doesn't matter that much. I mean, each of these is a probability distribution over the k possible groups. You know, so there's a simplex, a k-dimensional simplex of probability vectors that sum to 1. You could choose from in that uniformly. You could also start by having everything close to the uniform vector and then twiddle it a little bit with a little bit of noise and then do that. It appears not to matter very much. Okay? Yes?
Does it matter how you're doing the iterative update? Maybe all simultaneously or one after?
I don't think so. I mean, I know that we're used to worrying about, like, if we're updating a square lattice, we're used to thinking that if we do a synchronous update, we might get some funny checkerboard oscillation. But here, I don't think that's a big deal. I know people who do it synchronously. I know people who do it asynchronously. It seems to work fine in either case. Yes?
Does this algorithm break the symmetry that we were talking about?
So when it works, yes. So I'm about to talk about when it works and when it doesn't. But yeah, hopefully what happens is these messages become biased towards the truth. I should mention that when you finally, after you reach a fixed point of the messages, when you finally want to compute marginals, then you take all of the incoming messages into account. So you do the same thing, proportional to the same thing, but for all of the neighbors at each place. And that gives you an estimate of the marginals. Now, I should also say that if and when you reach a fixed point, you get an estimate of the 2-point marginals, the joint marginals of neighboring pairs. And in the block model, that's especially simple. So let me write mu super ij sub rs as the joint probability that vertex I belongs to group R and vertex J belongs to group S. It turns out that this is proportional to the following pretty thing. The probability that I tells J it's in group R times the probability that J says to group I, well, as a matter of fact, I'm in group S, times the probability that there would be an edge between them if they were. Okay? And then you normalize. Okay. Yes?
So when the algorithm converges, does the vertex I tell all of its neighbors with the same probability that it belongs to a group?
Not necessarily, no. No. In fact, imagine, since this is a sparse random graph, note that there will be an extensive number of vertices that are leaves of the graph. They only have one neighbor. And there are no other neighbors, and the product of the empty set is 1. Okay? You all know that, right? The product of all the elements in the empty set is 1. Good, okay. So in that case, this would tell its one neighbor that it was equally likely to be in every group. But based on the messages it receives from that neighbor, when we compute its marginal, if that neighbor is probably in group 3, this will probably be in group 3. Yeah. Yeah. So indeed, the messages remain different. All right. Now, let me just say a few words about why this is a good idea. So some of you have been at summer schools where I've lectured before, and I don't want to bore you with the same damn joke. You know, not that many of you, but anyway, maybe those of you who have already are outside checking their email. Anyway, I mean, passing messages back and forth between you and me and back to you, back to me and back to you and back to me, kind of pointlessly amplifies our biases. In fact, we have a paper about epidemic models, which is kind of nice. So I will not tell the usual joke about talk radio, which is what I usually say. An echo chamber? Okay, you can fill in the rest. So in an epidemic model, if I have a small probability of infecting you, but you have a small probability of infecting me, then initially, if each of us have a tiny probability of being infected, that echo chamber will raise, according to that naive model, the probability of us being infected until we both are. But that's silly, because probably at the beginning of time, neither of us were. And if we're the only 2 people in the world, then that would be a silly model, right? So somehow, the point is, am I going to pass an infection to you from my other neighbors? All right? But there's also a kind of deeper reason for adopting this, which is in answer to the question that was over here earlier. You know, why don't we just say everybody's marginal is a function of their neighbor's marginals? I said before that that is like assuming that the Gibbs distribution is a product distribution, which in our notation would be the product over all vertices of the marginal probability, whatever that is, of them being in that state. Okay? Now, it's perfectly reasonable to try to do things this way, and it goes by the name of naive Bayes. Okay? It's a perfectly reasonable approach, and it works reasonably well in lots of problems. It turns out, like I said before, that if you compute the callback-Leibler divergence, and I will not go through the details of the information theory, between this product distribution and the true Gibbs distribution, and you try to minimize that, well, remember in thermodynamics class when you learned that the Gibbs distribution is the distribution with the smallest free energy. Okay? The best compromise between the average energy and the entropy, where how much we care about the entropy depends on the temperature. Okay? Remember that? So there's this whole field called variational inference. And it's very popular in machine learning. And it goes like this. The real Gibbs distribution is this exponentially complicated thing with all these crazy high-order correlations. Product distributions are a very simple family of probability distributions with only a linear number of parameters. Okay? In the space of all probability distributions, the one which minimizes the free energy is the true Gibbs distribution. But let's look within a simple subset of all probability distributions, like the product distribution, and within that family of distributions, minimize the free energy. And it turns out that that's the same as minimizing the KL divergence between that distribution and the true Gibbs distribution. You know, thermodynamics is mostly just information theory. This is one of the parts of it which really is just information theory. Okay. Belief propagation corresponds to minimizing the free energy in a slightly fancier set of distributions, where we take correlations between neighboring pairs into account. So instead of just this, we multiply this by the product over all neighboring pairs of a joint marginal of those two. And then, to avoid overcounting, I'm going to divide away these one-point marginals. I apologize for the double subscripts. Okay? So this looks like a reasonable kind of probability distribution. You start with all the probability distributions of the individual vertices, and then every time they're neighbors, you take their correlations into account, whatever they are. Okay? So now we could ask you, within this family, you can twiddle all you like. You can set these one-point marginals to anything you want. You can set these two-point marginals to anything you want, except we better make sure that they're consistent. So we better make sure that if you take any two-point marginal and sum over the state of of one of them, you get the one-point marginal on the other one. Okay? Everybody see what I'm doing here? Okay. Subject to this consistency condition and the fact that all these probabilities sum to 1, if you minimize the free energy of this, you get a stationarity condition by taking derivatives. That stationarity condition turns out to be the same as saying that these messages are fixed points under that iteration. And the free energy you get then is the beta free energy. So I will not write it out, but it's not so bad. You can imagine, for instance, that if you're computing the entropy of this thing, well, you take the log and all these products turn into sums, and so there is a fairly simple expression for the beta free energy in terms of all of these messages. And that's an estimate of the free energy of the system. Now, there's a huge caveat here, though. Remember when I said that we're assuming that these two neighbors are independent except for the extent to which they interact through us? And I said, well, hopefully this is asymptotically true if all the loops are large. But it's only exactly true if the entire graph is a tree. Right? On a tree, then your neighbors really do interact only through you. It's worse than that. The beta free energy is a bit suspect because this thing here, I will leave as an exercise. You can do it by induction on the number of vertices. If we sum this over all spin configurations, it sums to 1 if the graph is a tree. If the graph isn't a tree, this doesn't even sum to 1. In which case, it's not even a probability distribution. So my claim before that we were minimizing the free energy among a family of probability distributions was actually totally bogus, unless the graph is a tree. So then, proving asymptotically that this is actually accurate, or that it's even an upper bound or a lower bound, takes real work and is a subject of active research. A question there, and then there, and then there. Yeah?
If we were to do this leaf propagation method on an arrow training graph, we would still get a segmentation. So does this tell us anything about how right our answer is?
You may or may not get a segmentation, which is what I'll talk about next. Yes?
How meaningful would it be to say there's groups on a tree?
Good question. Not very, probably. Well, actually, I know. Okay.
There are some examples.
Yeah, I mean, if you had a big bushy thing here and a big bushy thing there, and then one bridge connecting them, you could cut it there, although you have to be careful because everything on a tree is two trees connected by a single bridge. So I have had slightly passionate arguments with some of my friends about whether we can define community structure on trees. Yes. Not very passionate. Yeah.
Can you just put in the normalization as another constraint?
So Will Perkins and I spent a while on a visit to Santa Fe saying, well, gee, if we normalize this, however it ought to be normalized, we do get a sort of spin system where you could say that these result from external fields and that these result from two-point correlations. It turns out the following thing is kind of cute. Any fixed point of belief propagation, and as we'll talk about in a moment, there are typically multiple fixed points. If you normalize, this is exactly the Gibbs distribution, which struck us as bizarre because some fixed points are really right or close to right and others are really wrong. But the formula for beta free energy only works when z is 1, or in any case, its log over n is 1, so that the normalization is sub-exponential. So, all right. One more question. Yes. Yes, fine. I guess I'm here to talk to you all. What do you want to know?
So this extra term that we have is just extending it over the edges. Could we just continue that and extend over all the clicks?
Absolutely. And that would lead you to the Kakeya free energy. So, I mean, you know, this is sort of the first step, or maybe the second step, in a series of cluster approximations where we look at two-point correlations, three-point correlations, and so on. So if you wanted to look at three-way correlations, you would have messages, for instance, from pairs of vertices to the third vertex in their three-way. But so you can do this, and some people do. It does also get computationally more expensive, though. So, any other questions? Okay. You realize I'm joking, right? I want you to ask questions. But I also don't want to feel really guilty about not covering what I'm supposed to cover. Okay. So, we've written down belief propagation. And I've described it as an algorithm, and I've waved my hands and say, start randomly and update the messages until they reach a fixed point. Well, let me show you a fixed point. This says that everybody is equally likely to be in every group. Okay? You all tell me that you're all equally likely to be Democrats, Republicans, Greens, or Libertarians, and I do the math, assuming that those are equally likely a priori, and then I send similar messages out to all of you saying, gee, I'm also equally likely to be in any of these groups. So that's kind of a useless fixed point, though. And this gets back to your question about would we get a division. If this is the division we get, Well, physically, this is the paramagnetic state, right? This is the unmagnetized state. And if this is the fixed point I get, well, if you demanded a labeling, I would just be flipping coins, k-sided coins for everybody. Okay? And I wouldn't label things any better than chance. So let's call this the trivial fixed point, or you know, in one of our papers we called it the factorized fixed point. I'm going to call it the trivial fixed point or the silly fixed point. So I don't want to fall into this fixed point. So one question we should ask is, well, gee, is this stable? Okay. So if we start here, and indeed I claimed earlier that we could start our initial messages by perturbing this a little bit in some random way with a bunch of little vectors that sum to 0. Well, will I fall back into it, or will I fly away from it? And if I fly away from it, will I fly toward the truth, or just in some crazy random direction? Well, how do we do linear stability analysis? We think about the Jacobian. We look at the partial derivative when we do this update. Let's say we do it synchronously. We look at the partial derivative of all these messages with respect to all of these other messages. What's the next vertex after L? M? M's not a vertex. OK, all right. OK. Now, this is a huge matrix, but we shouldn't be intimidated by it, because what do we know? We know that the message from I to j is only affected by the messages coming in from i's other neighbors L. So, if you like Kronecker deltas, this is 0 unless I equals m, unless L is talking to I. It's also 0 unless L is not equal to j. Okay? And then finally, what's the derivative? Well, I leave it as an exercise that now the little k by k matrix of partial derivatives is exactly this k by k matrix, this little stochastic matrix. I want to give that matrix a name. I will call it gamma. It's just the normalized version of this matrix. Okay? So that's kind of nice. We've already got that written down. This is just gamma times RS. Okay, nice and compact. Now, we can also write this as the tensor product of two matrices. There's this thing, which is only interested in, well, who's talking to whom? So this depends only on the topology of the graph. And then there's this little k by k matrix that says, well, what groups are we talking about? And that depends only on the parameters of the block model. So I'm going to write this as B tensored with gamma, where B is this thing called the non-backtracking matrix. It's a lot like the adjacency matrix of the graph, which is 1 if two things are neighbors and 0 if it's not, except it's defined on directed edges in the graph. Okay? So mathematically, if you took the graph and you replaced every edge with two directed edges pointing in either direction, B is the matrix which says there is a matrix element of 1 going from this directed edge to that directed edge, but not if this one is just turning around and going back the other way, okay? And not if the head of this is not the tail of that. So B is just keeping track of which edges talk to which other edges, and the fact that the message from I to j does not depend on the message from j to I, the fact that we don't have that echo chamber, corresponds to this non-backtracking constraint. Okay? Everybody still with me? Who wants to be? Okay. All right. Good. Well, how do we tell whether this trivial fixed point is stable or unstable? You know how. All that matters is whether this matrix has an eigenvalue bigger than 1 in absolute value or not. That's when it's unstable. You also know that the eigenvalues of a tensor product are simply the product of the eigenvalues. So all we need to do is think about the spectrum of gamma, but we already know the spectrum of gamma. We know that it's a stochastic matrix and that its leading eigenvalue is 1. But let's think for a moment about what kinds of perturbations we're considering. It's a doubly stochastic matrix, and the eigenvector with eigenvalue 1 is just the uniform vector, 1, 1, 1, 1, 1, 1, 1. OK? That's its stationary distribution. But we would never consider a perturbation along the direction 1, 1, 1, 1, 1, because it would be like making all of these probabilities bigger, and the probabilities have to sum to 1. So if I sum this over R, it has to sum to 0, which means it's orthogonal to the matrix 1, 1, 1, 1, 1, which means the leading eigenvalue of gamma doesn't matter. The one that matters is the second one, which is lambda. OK? Good. Now let's think about the eigenvalues of B, this non-backtracking matrix. And beautifully blazoned on the web page of this summer school is one of the figures from the paper that several people here and I and several other people as well wrote. It turns out that the spectrum of B in the complex plane is quite lovely. So notice, by the way, B is not a symmetric matrix. So its eigenvalues are, in general, complex. Here's 0. So now, thinking of B as this, think of it as, well, one way you could think of it is as a branching process where every time you go along an edge, you're now on the next step allowed to go to all of the other neighbors of where you arrived. And then each place you arrive, you can go to all of their other neighbors and so on. And on average, this would branch with a ratio which is C, the average degree. You might be thinking, wait, shouldn't it be C minus 1 because it's all of the other neighbors? But let me remind you that if the degree distribution is Poisson, right? The fact that a Geiger counter clicked once in a second does not alter how many times it will click. Is this helping? I mean, OK. The point is that there are several ways to say this. The algebraic way is to say that if I have a Poisson distributed random variable, and I guarantee that it's at least 1, and then I ask how much more do I have, it's again Poisson to the same mean. The physicsy way is to say what I was about to say before I abandoned it, which is that if a Geiger counter clicks at the beginning of a time interval, it has no effect on the expected number of times it will click in the remaining time interval, and the number of clicks is Poisson distributed. And the probabilistic way to say it is to say that the definition of our random graph is that you're connected to each other vertex with an independent event. So the fact that I'm your neighbor and that I arrived at you coming from me does not in any way affect the probability that you're connected to a bunch of other people. All right. I say this because yesterday one of you asked, well, what about degree distributions other than Poisson? And then the answer to this average branching ratio question wouldn't be the same as the mean degree. OK? But it is. So the leading eigenvalue is just C, the average degree. But does this eigenvalue matter? No, because the eigenvector corresponding to this is roughly uniform on the graph. And a perturbation in that direction would be like pushing everybody's label toward the same group. And then the non-edges come in and say, no, you can't do that. So remember, I told you I would sweep them under the rug except when they were useful to me. This rug appears to be tacked down, but I will tear it up, pull it back out, and say, if we do take the non-edges into account, they suppress the eigenvector corresponding to that eigenvalue. OK, good. So what's left? There is a bulk of random-looking eigenvalues inside the disk in a complex plane of radius square root the average degree. And this is very much like a complex version of the semicircle law that Giulio told us about yesterday for random Gaussian matrices. It's trickier because these are sparse matrices with 0, 1 entries, and it took some experts in random matrix theory, Bordenov, Lelarge, Massoulier, to make this rigorous, but they did, and it is. OK? So these eigenvectors, though, are effectively random. And if they're the ones that take over when we iterate a small perturbation, we won't get anywhere. We'll get something which is not correlated with the truth. Well, there is one more eigenvalue I need to tell you about. I'll call it mu. Oh, I already used mu for something else. I'll call it eta. OK? And this one equals C in minus C out divided by K. And this corresponds to an eigenvector which is different on the different communities. OK? So for instance, if there are only two communities, this corresponds to an eigenvector which is mostly positive on one community and mostly negative on the other. OK? We like this eigenvector. This eigenvector would tell us something about the community structure. OK. I'm going to pause here to mention something that you may have heard of, which is another popular clustering method for networks and graphs, and for lots of other kinds of data sets as well, which is spectral clustering. How many of you have heard of spectral clustering? OK, so what's the idea of spectral clustering? Classically, you do it with the adjacency matrix or the graph Laplacian. And let's say that you have a graph here which consists of these two tightly connected components with only a few bridges crossing between them. OK? Imagine doing the heat equation on this graph, or a random walk, or diffusion, which all amount to the same thing. What would be the slowest mode that would take you the longest to get rid of in order to reach equilibrium? It would be the one where these are hot and these are cold, and these have mostly equilibrated and these have mostly equilibrated, and slowly we're adjusting the temperature between the two. And so if you look at a lot of classic linear operators associated with graphs, their second most important eigenvector is something like this. OK? And so a popular method is diagonalize the adjacency matrix and look at the second eigenvector and just, label things according to whether it's positive or negative on that vertex. OK. In fact, this does not work for sparse random graphs for reasons that I'm not sure I want to talk about. But it gets fooled by localized eigenvectors that show up inside the graph. For instance, if by chance you have some vertex with rather high degree, which you will have by chance, there's a localized eigenvector which just spends all of its time near here. And so it would be high there and then would decay exponentially, and it would not have this nice global structure we're looking for, where it's, say, positive on one community and negative on another. But the non-backtracking matrix works in the sparse case, because by preventing backtracking, you're not allowed to just go back and forth between a high-degree vertex and its neighbors. So the upshot is the eigenvalue of gamma that matters is lambda, which is written over there. The eigenvalue of B that matters is eta, which is written over here. And what matters is when lambda times eta crosses 1. And this is the threshold for this trivial fixed point becoming unstable. And when we write that out, if we notice that actually eta is c times lambda, we get c lambda squared equals 1. And this is this thing called the Keston-Stigam threshold. And there are actually two different things here that happen at the same time. One of them is that the trivial fixed point becomes unstable, and so belief propagation will tend to fly away from it. But the other thing that happens at the same time is that eta crosses the boundary of this bulk. If I set eta equal to square root of c, which is the radius of this disk of bulk eigenvalues, well, notice that if I set this equal to square root of c and divide both sides by square root of c and then square both sides, I get c lambda squared equals 1 again. This is good news for us because it means that at the same point where the trivial fixed point becomes unstable, this informative eigenvector is the one that we fly towards. Now, so far, all I'm really telling you is that if we start at the trivial fixed point, so this is now our high-dimensional space of messages, and you perturb things randomly, you'll fly towards this dominant eigenvector, which is correlated with the communities. Belief propagation is a nonlinear process. It's only linear to first order. Everything is linear to first order. But it turns out that the fixed point we arrive at is not so different from the eigenvector of this process. And so then we arrive at a set of messages which give us marginals, which are correlated with the true planted state, and we succeed in solving the community structure problem.
So does that mean that you can avoid doing the annealing and just go to that eigenvector?
Indeed, in this paper, we proposed using spectral clustering and skipping belief propagation. It does almost as well. So the accuracy you get, defined, for instance, as the average marginal probability assigned to the true spin, is not quite as good as what you get from belief propagation. Belief propagation, we believe, is asymptotically optimal. The spectral clustering method does almost as well. Okay.
Question?
Yes?
Would you say that the informative fixed point is a stable one?
Well, right. Now I need to tell you. I need to tell you more. Right. So I haven't told you sort of where we end up. I only told you this analysis only tells us in what direction we head away from the trivial fixed point. It doesn't tell us quite where we end up. And therein lies the last part of my lecture. Patrick.
So does it make a good first step? So if you start with a guess that's 1 over k, and then you calculate the spectral matrix, and then you run belief propagation, you converge very, very fast. Is that the idea?
We think that's the idea, but I don't know if Florent has gotten around to coding it up. You're right that a smart way to initialize belief propagation would be with the messages suggested by the spectral method. And so, yes, we think that would help. Did you ever write that up?
That's the canonical implementation we have, right?
Oh, that's already what we do?
Yes.
You can tell that I'm not so active on the coding side of this paper. Okay. Now, there is more to the story, which is going to reconnect with the glacier stuff. Okay. When there are only two groups, what I've told you is pretty much the whole story. If this y-axis here is the accuracy, the fraction of vertices we label correctly or whatever, when c lambda squared is bigger than 1, you do well. When c lambda squared is less than 1, there's nothing you can do. And although I don't have time to prove it to you, again, on this side of the threshold, it's information theoretically possible to label the vertices better than chance, or even to distinguish the graph from our null model, our Erdős-Rényi model. Okay? I will not prove that to you, unless you make me do it over lunch. When there are more groups, though, some additional phenomena appear. You might think, 2 groups, 3 groups, 4 groups, big deal. But you might know that the k-state Potts model has a first-order transition when k gets large enough. So when k is bigger than or equal to 5, or 3 or 4 sometimes, for some values of the parameters, we get something else happening. So first, let me show you what happens if we initialize belief propagation with random initial messages. Okay, so now we see a discontinuous jump in our accuracy. And what happens is above here, the trivial fixed point is unstable, and we do well. Okay? But belief propagation can have multiple fixed points. And it can also have multiple stable fixed points. So now let me show you what happens if I magically initialize things, if I cheat. We're just going to cheat, and initialize belief propagation with the true types. What's going on? What's going on is that there's another stable fixed point out here, which is accurate. And there's a regime in here where both the trivial fixed point, which is accuracy 0, or overlap 0, as Giulio said yesterday, and the accurate fixed point. So what's happening here is that if you think of belief propagation as doing gradient descent on a free energy landscape, which is essentially what it's doing, it's the beta free energy landscape, but it's the same thing, really, is that in this regime, the trivial fixed point corresponding to the paramagnetic state is locally stable. There is a highly accurate fixed point corresponding to the single true cluster. Okay? But unfortunately, it has a very narrow basin of attraction dynamically, so that if we start with random initial messages, our chances of finding it are exponentially small, and almost all initial messages will instead fall into the trivial fixed point. If we had exponential time, and we could really explore the entire landscape or run belief propagation exponentially many times, we would find it. But if we have only polynomial time, we believe we don't have a chance. 1 second. Let me just tell the rest of the story. The Keston-Stigum transition is a spinodal transition. Unfortunately for you, if you're taking notes, it's a spinodal transition that does not exist in the p-spin model. It's where the 0 overlap state, the paramagnetic state, becomes unstable. Okay? And so if you like, this goes from being a local minimum of the free energy to a local maximum, and you fall away from it into the accurate fixed point. Then there's a point here, which is the Kautzmann transition, also the condensation transition, where, like here, both of these fixed points exist. But now the accurate one, this is in this regime, The accurate one actually has larger free energy, and that means that even if I showed it to you, you would say, well, yes, but the chances of this being the truth are exponentially small, so I don't believe it. And once we cross this point, if you had to guess, you would say, oh, this graph is just an Erdős-Rényi random graph. There are no communities, really. So this point here, which is the Kautzmann transition, is also the information theoretic threshold for community detection. And then below here, this accurate cluster doesn't even exist. And this is the other spinodal transition that does exist in the p-spin model. Okay? So, I mean, if you want to think of this in terms of the Franz Parisi potential, in a certain sense, the more strong the community structure is, the larger that potential is. When the community structure is strong enough, then we are drawn into the accurate fixed point. When it's really strong, we're drawn into it dynamically. When it's strong enough, we are drawn into it in an information theoretic sense if we could magically sample from the entire distribution. But that would take us exponential time, and there's a free energy barrier here that we think would take us exponential time for Monte Carlo to cross, and so on. So here, it's possible, but we believe it's hard. We have not yet proved that. We don't know that P and NP are different, but we could hope to prove it for important classes of algorithms. So lots of people, including me, are trying to prove that Monte Carlo really will take exponential time starting from here, starting from a uniform initial state. And we're trying to prove the claim I made before, that only an exponentially small fraction of initial messages will get there from belief propagation. Okay. In this case, it's easy, and on this side, it's impossible to find the communities or tell if they exist. Let me pause for questions here. There's one more thing I want to tell you. But first, any questions about this picture? Yes?
So your belief propagation is a minimal fluctuation, right? Otherwise, you start at the true position, it would just stay there free.
Well, of course, even the true position, I mean, it wouldn't stay exactly there. There is some uncertainty, right? So, I mean, even if I start at the, I mean, it's still finite temperature, right? So the accuracy even up here would not be 1. I mean, after all, by chance, some people have more neighbors in a different group than in their own group. Okay, so, we can't ask the algorithm to label such nodes correctly. Yes?
So this, I call it this algorithm. This move is deterministic, right? You still have to cast it into a Monte Carlo relay.
Well, it is in a sense, it is a deterministic procedure, but these are all real numbers, right? So the interesting thing is that, I mean, Monte Carlo, at each moment, the algorithm's state is discrete. It's an actual label or spin for each vertex, and then we update those, and then do this for a long time and measure statistics. Belief propagation is doing something different. It's the state of the algorithm is a set of real numbers describing these messages, and we update these real numbers with a continuous procedure. And the hope is that those real numbers, when we reach a fixed point, give us the same marginals that we would get if we did Monte Carlo for a very long amount of time. Does that make sense? I mean, there's still non-determinism in the choice of initialization. And, I mean, there's a little bit of non-determinism if you decide to update things asynchronously. But I think that's not actually, that second kind isn't important to us.
Another question, maybe I missed that. Did you say that by calling this deterministic move, you always lower the free energy?
This is a kind of what you would call coordinate descent. It's not exactly gradient descent. So coordinate descent is when you have a function of a bunch of variables, and you ask about each variable, if I kept the others fixed and varied this one, how could I minimize the function? So if you do that with a discrete jump, you might actually increase the value of the function. But in practice, lots of people don't jump directly from here to here. Instead, they use some kind of damping factor and move the old message toward the new message, and then it would be more like gradient descent. So that's something that you could do if you saw things getting crazy numerically. You would add that damping and just update the messages a little bit. There, I proved that I sometimes do code this algorithm. Yes? This is a bit mysterious. I claim that in this regime it's still impossible because what's happening is there is a true cluster, but there are also many other clusters that look equally good. Okay? So if I told you this was the true one, why would you believe me? And thermodynamically, the system is dominated by these clusters that are not correlated with the truth. So for instance, the free energy, okay, this is something that Florent really wanted me to say. The free energy of the planted model and the unplanted model are the same up to this point, up to the Kautzmann transition, where the true cluster's free energy crosses that of the paramagnetic state. Okay? So if you had this sort of godlike ability to look at the entire landscape, you would say, gee, it's bumpy, there are clusters, something's going on. But the point is that the same thing happens even in the Erdős-Rényi graph. Okay? So the same dynamical replica symmetry breaking happens when the Erdős-Rényi graph gets, when its average degree gets large enough. Okay? So you really wouldn't have any way to tell the difference between the two. All right, I'm going to conclude with, since I began, actually this is a nice segue. So remember how I began by saying, oh, even random graphs have good-looking community structures, but they have many of them and they're not correlated with each other. That's right in this region here, okay, where we have had dynamical symmetry breaking, but not a true thermodynamic transition. And so that brings me to this question, since I said then, oh, if I showed you that community structure, you would be convinced, but we would just be overfitting. Okay? And overfitting, people love to overfit. We all want to see patterns, whether or not they're there. Right? We crave patterns. We would rather think that there's a tiger when there isn't one than think that there isn't one when there is. So we were evolved to avoid false negatives more than false positives. And, you know, if you're a young molecular biologist and you need to get a paper in Cell in order to get a job, then, or in Nature, then by God, you need to find a correlation between some gene and some disease, even if it isn't really there. Okay? So we have lots of incentives, evolutionary and professional, to find black cats in dark rooms even when they're not there. So what happens if you're overfitting in this setting? I want to draw you a phase diagram. This will be my last thing. The x-axis here will be this quantity, c lambda squared, and this is the true one. Okay, in other words, I'm going to make a graph for you generated by this stochastic block model where this is the true level of community structure in the graph. But I'm not going to tell it to you. Okay? Remember yesterday I said, we'll assume you know all the parameters. Well, now we will not assume that you know all the parameters. But you know it's in this family, so you say, okay, I'm going to run belief propagation, I'm going to do my inference, but with a possibly different value of lambda, and this will be the one you assume in your algorithm. This diagonal line is when you have the right parameters. It is also the Nishimori line. So you'll probably be hearing a lot more about the Nishimori conditions later. But, and this came up kind of implicitly in Giulio's lecture yesterday, a very important fact about this model. If you have the right parameters, if you know the right model, a very important fact, which is sort of, it's written somewhere, it's right here. Saying that the probability of the probability that a given configuration is the true configuration is the Gibbs distribution. Well, that's the same as saying that the planted configuration is a typical draw from the Gibbs distribution. It's the same as an equilibrium distribution. It's the same as an equilibrium state. Okay? And that's the Nishimori condition. But if we have the wrong model, that is not true, or might not be true. So, let me just focus on the case of two groups so that we are in this simpler situation instead of this more complicated one. So in this case, the dynamical transition and all these transitions coincide. The algorithmic one and the information theoretic one.
Could you just repeat also 3 and 4?
What? Oh, well, 3 and 4, it depends on the parameters. If it's antiferromagnetic enough, then you get this even for 3, right? Or even for 4. For 3, it's always like this. I'm always getting this wrong, and I'm always having to email. And we got it wrong, and we published it wrong in one of our papers. OK. For 2 and 3, it looks like this. For 2, that has been proved. For 3, it has not yet been proved. For 4, it looks like this when the model is sufficiently antiferromagnetic. OK. Too much information. It's lunchtime. Let me draw my phase diagram. So, to the left of this line, there's nothing you can do, nothing accurate you can do, because this is the true detectability transition using the true parameters. On the other hand, when this is bigger than 1, the trivial fixed point becomes unstable. Well, it's unstable, but we know that we're to the left of the detectability transition, so what happens? Well, what happens is that it's one of those bulk eigenvectors which we fly out along, and those are random. So we fly away from the trivial fixed point, but in a random, unhelpful direction. And what actually happens when we iterate belief propagation is it fails to converge. It jumps all over the place. It never settles down. And what belief propagation is trying to tell us is, I'm in a spin glass phase. I'm jumping all over the place from one local optimum to another, and I can't find my way around, and there's nothing I can do. Okay. On the other hand, so that's what happens if you overfit. If you look too hard for structure, if you look for more structure than is really there, you're getting too greedy. By the way, you can also think of this as the inverse temperature, right? Because colder means more structured. And so this is like saying, I'm going to too low a temperature, the landscape is getting very bumpy, and now we're really in a spin glass phase. And we think here there's like full RSB. On the other hand, if you set your temperature too high, you assume too little structure, you will underfit. And in this entire region, you get this paramagnetic phase, meaning that you get this. You just evolve towards the uniform fixed point, and you don't see any structure. You're underfitting in that case. And then there's this region here where, including when you have the right parameters, but there's also a fair amount of freedom, where you do get this phase corresponding to the ferromagnetic phase where you do evolve towards an accurate labeling. So this is a nice phase diagram showing the danger of overfitting and underfitting, and Panjang and I proposed this as a kind of physicsy way to tell when you're overfitting and when you're underfitting. I'll take one more question, but it's 12:30 and you're hungry. What's your question? Really? Okay.
I do have a question.
Yes.
I want to kind of think of extending this model. What if at the beginning you don't even know the number of groups?
Then that's complicated. So yeah, how do you tell the number of groups? You can look for, one method we proposed is how many real eigenvalues does the non-backtracking matrix have outside that disk? That's one method. There are more Bayesian methods. In our earlier paper, we talked about looking at the free energy. So as you increase the number of groups at a certain point, the free energy flattens out. But people argue about this. There are people who say you should use the minimum description length, which is a little bit ill-defined. There are people who say you should use the Aka-Iki information criterion, which is wrong in the case of sparse networks. There's all sorts of arguments about how to do model selection. One general way is cross-validation. Hide some of the data from me, see if I can fill it in. If I can do that well, then I know something about the data. And typically, if I use a model which is too elaborate, my ability to do that actually degrades. So simpler models will often generalize better than more elaborate models. And so if I have too many groups, then my ability to fill in missing links will probably go down. All right, thank you very much.